Finite to infinite is one truth of nature. Just a small finite set of elements are the source of infinite compounds. There are infinite precise or mathematical combinations of these elements in the form of compounds. The same is true for colors. In one model called the RBG of red, blue, green colors, we create a vast spectrum of colors from this limited set of base colors through mixing and blending. Pertinently, in mathematics, a small set of functions, best called the parent functions, can be used to compose infinite number of functions to best suit the realities they are to represent. Welcome to crafting functions, making composite functions out of the parent functions. To the point, functions are not all standard, fixed, and crafted anew by mathematicians. The reality is, functions are used to mathematize everyday life situations, and we all can create the mathematical equivalent of the everyday situations. We use a set of functions, the parent functions, as the base to create or compose more. We will explore some of these composite functions. Simply put, the composed functions are arithmetical combination of the parent functions. I may remind that the set of 11 parents functions I use is kind of my choice, one that best fits the scholastic needs of the school years. Before we take the plunge into the world of composite functions, we must explore a couple of elementary examples of how real-world situations push us to create new functions, using arithmetic operations on functions. Consider a water bottling plant. It has two key operations, filling and capping the bottles. Of course, there are other steps, such as cleaning, labeling too. If the filling of water is considered as one function, say F, relating time and quantity of filled water, and capping the bottle as another function, say G, then the quantity of water bottles produced in the plant is a result of these two steps. Next, these two steps, in terms of functions, can be considered as a combination function as F plus G, where plus is a replacement of and mathematically. The combined function gives us the quantity of water bottles produced in a factory and the time taken for it. In this case, the output function, or the function of production for sales in a period, is simply the sum of two functions. As another example, and one that is a bit of interesting form of combination, consider a situation where we work for 20 hours a week at some store and receive $5,000 as the weekly salary, plus a 5% commission on the weekly sales over $1,000. The currency denomination is immaterial here, thus not mentioned. Suppose we sell enough this week to get the commission. Then how can we describe the commission amount through a function, that is, through a mathematical expression of input and output? We may describe the situation by using two functions. One for the commission amount as a percentage of weekly sales, say X, and the other for the commissionable weekly sales, the weekly sales value on which commission would be computed. Let the commission function be called Fx, and it is equal to 0.05 of the commissionable weekly sales, and in turn, let the commissionable weekly sales function be Kx, and it is equal to X minus 1000. In other words, we take the weekly sales, X, subtract off 1000 on which we do not get commission, and then take 5% of the reduced sales amount. This is equivalent to 0.05 of X minus 1000. And using functions, it is F of X minus 1000 or F of Kx. In this case, the new function is a nested one. We use one function, Kx, as the input to another function, Fx. Hopefully, we get some sense of how new functions are created by combining functions. We are now ready to see some composite functions made out of the parent functions we discussed, and we are ready to rush headlong. To keep it all simple and contextual, we will graphically visualize the combined function to best see the unique behavior of the composed function compared to the parent functions creating it. We have to keep it all intuitive and thus use simple visual observations to see the effect of combination of functions. The idea is to just get a feel of the combined effect through graphs. This is the combination function fx equal to x plus log x. First, this is the graph of fx equal to x. Second, this is the graph of fx equal to log x. Third, this is the graph of fx equal to x plus log x. This graph is unique and shows the effect of the addition of the x coordinate at every point on the log x, and kind of pulls up the graph of log x. This is the combination function fx equal to x minus log x. We are only showing the combined function graph. Did you expect the graph to be this way? Without getting into the detailed mathematics, it is noticeable that when x is 0, x minus log x is plus log x value at x equal to 0. For minus of minus is plus, log x is negative at x equal to 0. And that what we see in the graph of x minus log x at x equal to 0. This graph is unique. The graph shows the combination function fx equal to x log x. Clearly it shows how the multiplication of x coordinate values significantly increase the log x at each point on the x-axis. Now we see the effect of combining linear function fx equal to x and sine x. The combining arithmetic operation is addition, that is, the combined function is fx equal to x plus sine x. First, it is the sine x graph. Second, it is the familiar fx equal to x graph. But to better explain the effect of adding or subtracting from x, we are showing x plus 1 and x minus 1 graphs. The graphs show how the graph of fx equal to x shifts up or down with addition and subtraction on x. Third, it is the combined x plus sine x graph. The combined function graph is easy to visualize. It is simply shifted along the fx equal to x graph, kind of pulled along by the fx equal to x graph. This is another kind of combination. X plus e to the power x. First, the familiar fx equal to x. Second, ex graph. Third, x plus ex graph. This is also easy to visualize. For example, at x equal to 0, x plus ex will have the value of ex alone. And that is what we see in the combined graph. The value of ex at x equal to 0 and the value of x plus ex at x equal to 0 is the same. Combination function 7fx equal to x plus ex. This combination function is fx equal to sine x plus log x. First, this is the sine x graph. Second, this is the log x graph. Third, this is the combined function graph, that of sine x plus log x. This is easy to visualize again. We can observe two things to kind of affirm the combined effect. First, at x equal to 0, the value of sine x plus log x is same as that of log x, as sine x value is 0. Second, the log x is pulling up the sine x graph, as obvious from the fact that the amount of combined graph in the fourth quadrant is reducing. Despite using simple observation of the combined functions graphs, we can see how the combined graphs do represent the arithmetic combination of the individual functions in it. Graphs are a very handy way of seeing the combined effect of functions. Of course, data sets of the combined function can also be used to see the combined effect. Also, it is easy to realize that we can play with functions and their combinations to get the most desirable new behavior of combined functions. For example, sine of x by 4 plus log x is going to be very different in behavior compared to sine x plus log x. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.